Okay, we've been given these 4 different solids here, and there's 1 mole of each, and they're dissolved in solution, and they form ions in solution. And we have to say which solution contains the most number of ions. Okay, well, let's work out what ions are going to form when they're in solution. So what have we got here? Well, we've got an SO4, that's a sulfate, okay, which has a 2- charge, so that's going to be floating around by itself when it's in solution. And we've got 2 ammoniums, so we've got an NH4 and another NH4. Each of those will be +1. So 2 + 1 is a +2, balancing the 2- of the sulfate. So that will form 3 ions in solution. Okay, right, what about iron chloride? Well, we're going to have the iron atom, which is a 3+, because it's got 3 chlorines on it, and 3 chlorides, because there's 3 of them, each has a 1-. So that's going to form 4 ions in solution. Right, magnesium nitrate, we will get a magnesium, 2+ charge, and 2 nitrates, NO3-, NO3-. So that's 3 ions. And potassium bromide, well, it's just going to be K+ and Br-. So that's 2 ions. So the winner is this one, because it forms 4 ions in solution. Iron chloride. There you go. Okay, devise a plan. Oh, God, they're so boring, these sort of questions. You've just got to turn the handle, churn out the same old rubbish they ask for every time. Devise a plan to compare temperature changes when sodium hydroxide is neutralized with 2 different acids, 4 marks. Okay, so the 2 acids you've been given, they're the same concentration, and you've got some sodium hydroxide. So we're going to add these 2 acids to sodium hydroxide and see which one increases the temperature the most, basically. Okay, 4 marks. Let's get this over with. So first thing, measure out 2 identical volumes of the sodium hydroxide. Okay. Next, measure out the same volume of each acid. Same volume, same concentration, therefore same number of moles. Same volume of each acid. Okay. Next, record initial temperature of the 2 sodium hydroxide solutions. Okay. Next, add each acid to each sodium hydroxide. Each acid to each sodium hydroxide solution. Okay. Obviously you have to write this out in full sentences in the real thing, but I'm doing it shorthand. Right, stir, allow to settle. And then finally record final temperature of each solution. Temperature each solution. And that will get you your 4 marks. Same sort of thing with all these sort of questions. Okay? Right. Oh, and if you like, you can say something like compare temperatures, compare temperature changes. Just to absolutely nail in those 4 marks. Okay. Right. So So we've got to draw a reaction diagram for an exothermic reaction. Let's have a colour change. So it's hydrogen reacting with chlorine. Okay, so H2 plus Cl2 making 2 HCl's. And we're told this is exothermic, so there'll be heat there because it's exothermic. Okay, right, so we've got to fill in this for 3 marks. Exothermic reactions. So firstly, draw a line like that and get it flat, okay? And then there's a hump, and exothermic reactions finish lower than they started and finish it flat like that, okay? So heat energy. And I've called this progress of reaction. Okay, so exothermic reactions look like this, and while we're at it, I'll quickly draw an I'll do it in this space here, why not? Endothermic reactions go like that, okay? That's endothermic. That's just extra information, okay, for your revision. It's not part of this question, but endo looks like that and exo looks like this. Okay, right, we have to label the activation energy. So you do a little dotted line across there, an arrow from the dotted line to the peak, and that is the activation energy, okay? Always put that down. Also, label the reactants here and the products end up here. So let's actually say what they are. That's H2 plus Cl2. The products, or yeah, it's 2 HCl. Okay, that's what an reaction energy diagram looks like for an exothermic reaction. Endothermic, okay, the activation energy is not from there to there. Activation energy for an endothermic reaction is that, okay? Activation energy. Good. Okay. So that's what you need to do to get your 3 marks. Right. Change of colour because that pen is pants. Right, finally. Bond energies. We've been given these bond energies, okay, for an HH bond in the hydrogen, a Cl-Cl bond, and the HCl bond there. Calculate the energy change of 1 mole of H2 reacting with 1 mole of Cl2 to make 2 moles of HCl. Right, no problem. To do this, if it helps, you don't need to do this, but I would recommend it. Draw, so this is the reaction we're talking about. It's the same one for this question, okay? Draw underneath what the actual molecules are that you have, then you can see the bonds. So an H2, okay, it looks like this. It's H, H. H2 is a diatomic molecule. It's one hydrogen, single covalent bond to another hydrogen. Plus Cl2, same thing, diatomic, Cl, single bonded to a Cl. Okay, it goes to 2 HCl's. So HCl there and an HCl there. Big 2, there's 2 of them. And it balances. That's why that big 2 is there. You need 2 of these. For one of those, you have to get 2 of these. You can't just have 1 HCl forming because there'd be 2 hydrogens on that side, two hydrogens going in but only one coming out. You need two going in, two coming out. Same with the chlorines, two going in, two coming out. So now you can see the bonds. We have one HH bond, okay? There it is. So that's 436 kilojoules per mole. We have one CLC bond, one ClCl bond, which is 243. Okay, I'm going to add them up. And on this side, in the products, we've got 432, but there's two of them, so it's 2 times 432. Okay, the 436 plus 243 is 679 on that side. Okay, and 2 times 432 is 864. 864 kilojoules per mole. Joules, big J, per mole. Okay, right, so the difference between 864 and 679, so 864 minus 679 is 185 kilojoules per mole. But we have to make sure we get the sign right, okay? Is the answer going to be plus 185 kilojoules per mole or minus 185 kilojoules per mole? Okay, think of it like this. When a reaction takes place, these bonds here have to be broken, right? And that's why you put energy in. That's why there's an activation energy. You need to put energy in to get over that hump to break these bonds. And then when you've done that, the products form, and these two bonds here are formed. So that bond is formed, and so is that one. Okay? So what we're doing, we're putting in 679 kilojoules of energy per mole. So that's a plus, right? That's on this side, the left, that's what we put in. When these bonds form, okay, that energy is released. That's released out. So that's a minus, okay? So that's how you know which one's plus and which one's minus. So we do plus 679 minus 864. So overall, so it's plus 679 minus 864, which equals, what did I say? So overall it's negative. It's minus 185 kilojoules per mole. Okay? You won't get full marks if you get that sign wrong. Good. And that's it. Now, I just want to say one more thing. Because this is an exothermic reaction, you were told it was an exothermic reaction. You know it's going to be minus, okay? For exothermic reactions, this is always a minus. That minus shows that energy is released into the surroundings as heat overall, okay? So you kind of knew it was going to be minus anyway, but it's important to realize why it's minus because of what I talked about, okay? So for an exothermic reaction, it's negative. For an endothermic reaction, it would be positive. Great, there we go.